Thanks for the opportunity to talk about this research. So I'm going to talk about improved quantum and quantum-inspired algorithms for semi-definite programs. And I used to be at Inria, one of the partners of Equality, but now I've since moved to the University of Copenhagen. And I should also say that this is joint work with people in Cambridge and TII. So why should people in industry care about this talk I'm going to give right now? So if you look at many industrially relevant problems, say in network design or logistics, chip layout, risk management, many other things, it is not uncommon that when you actually try to find optimal solutions or good solutions, you end up mapping them to very large combinatorial optimization problems. And combinatorial optimization problems are often very hard to solve, both from a computer science, like theoretical perspective, but also in practice. Now, of course, there are many different approaches to solve combinatorial optimization problems, which is not surprising given their relevance. People even construct hardware that has the sole purpose to solve them. Think of maybe like quantum annealers, like the D-Wave machine, or the digital annealers, like the Fujitsu one. So there's a lot of effort to try to solve these things. And moreover, there are methods that allow us to efficiently solve not efficiently solve, but efficiently approximate these combinatorial optimization problems through convex optimization problems. And convex optimization problems are typically efficient to solve in the number of variables. And for combinatorial optimization problems, usually these convex relaxations take the form of semi-definite programs. Now, in practice, solving large semi-definite programs remains challenging. So if you're already looking at problems with a few hundred, a few thousand, or maybe a million variables, you quickly run out of memory. And this then doesn't stop working anymore. But nevertheless, we would like to be able to solve or get approximate solutions for these combinatorial optimization problems at larger scale, so that we could unlock better schedule, lower costs, and so on. Now, this talk, I'm going to talk about a very specific form of combinatorial optimization problems, namely QUBOs, which are quadratic, unconstrained binary optimization problems. And for those, you're given some symmetric matrix C, and you want to maximize this scalar product over here. And this is NP-complete, but a very common problem. So NP-complete means it's hard to solve, but they pop up in many applications. So for instance, if you think of the max cut of a graph or finding the ground state of an Ising model, they can be easily cast as such QUBOs. Now, there is the so-called Goemans-Williamson SDP relaxation. And it sort of relaxes this problem and replaces these binary constraints, which are very discrete, right, into a matrix constraint, which is the following down here. And this you can solve in time that is a polynomial in the number of variables, whereas this QUBO, in general, we expect exponential time to actually, in n, to solve them. And these SDPs, they give you a way of getting an upper bound on what is the best possible value this can take. And they also give you a way of doing a so-called randomized rounding, which will also give you a feasible point of this problem, which so a minus 1, 1, plus 1, 1 vector, that is guaranteed to be at least 87% of the optimal. So you get an upper bound on how well any solution can perform, and you get a feasible point that is sort of not too far from that. So within 30% of the optimal, sometimes it's better. Now, as I said, even though this is in principle polynomial, like solving these problems, you still need to store some dense matrices, and you quickly run out of memory. when you try to solve them in practice. As we'll see in a few seconds, I'll show you a plot that demonstrates this. And on top of that, at least for previous, and then because of this, you might think that maybe quantum algorithms could help us to solve such optimization problems. And if you squint at this optimization problem we have over here, it's like an optimization problem over matrices. And these matrices have to be positive semi-definite. So I don't have the time to actually explain the connection to quantum here, but you can massage such problems into simulating a few Gibbs states, quantum Gibbs states. But the previous quantum algorithms that people found to try to solve these optimization problems, they have some serious issues. So for instance, they have a very poor scaling in the accuracy of the solution you get. So you need to identify problems where getting very rough solutions is already good enough. And they required the preparation of so-called quantum Gibbs states of the following, which are states of the following form, for unphysical Hamiltonian. So H here is just like a big matrix, which may be sparse, but you don't know more than that. And in general, we don't expect quantum computers to give exponential speedups for such unstructured problems. We need a more physical structure to actually get exponential speedups for quantum computers, generally speaking. Now, in this work, we look at very special instances of these semi-definite programs. So in many real-world applications, these matrices C that define your cost, they are very structured. So they usually are sparse, or they have some repeated blocks or things like this. And we go one step further, these sort of sparsity assumptions, and consider matrices C that can be written as a sum, weighted sum of a few Pauli strings. So in the sense, C looks like a quantum Hamiltonian, which usually admits such as decomposition, right? On top of that, we further relax the constraints of these semi-definite programs and are able to show that if you do this in a smart way, and the smart way depends on this particular decomposition of the Pauli strings, we are able to reduce significantly, sometimes even exponentially, the number of constraints you need to solve certain semi-definite programs. And on top of that, we are also able to reduce solving these convex optimization problems to studying properties of certain quantum many-body states. So now we started from a convex optimization problem and reduced it to solving a problem in quantum. And then we can draw from techniques to simulate quantum systems on quantum computers. But we are, of course, not completely in the dark also classically, and have non-trivial simulation methods for these systems. So in particular, we are able to run our algorithm using tensor networks on certain instances and solve huge STPs, so semi-definite programs. So we solve STPs with up to 2 to the 50 variables. To the best of my knowledge, this is the largest STP people have ever solved. Again, these are highly structured instances. These are not generic instances. We need extra structure to be able to map it to quantum systems. But we are able to solve them at much larger scale, and we're also able to compare with other methods. So let me zoom into the plot to explain a bit better how our results compare. So I zoomed into the upper left corner of this plot, and just to explain to you what you're seeing. So these blue dots, okay, these are the certificate as to how well any solution ever you could think of could perform for this quadratic binary optimization problem, okay? So each dot represents adding 1 qubit, which means we are doubling the number of variables we're considering, Okay, and the red dot is the feasible point, a feasible solution we found using our methods. This means that sort of the blue represents the best you could hope for. Maybe this is not the optimum, but definitely the optimal solution will not be better than this. And the red one is a point we found. So we see that they're pretty close. Now, these dark black circles, they correspond to solutions found with heuristic solvers to this binary optimization problems, in particular taboo search. So we see that they indeed find better solutions that our method found. So our method is the red dot. These are the black dots. However, the difference isn't insanely big, as you can tell. And on top of that, they already stopped working at these sizes, right? So we can go significantly further than these heuristic methods without losing much. And the gray dots are previous state-of-the-art STP solvers based on sketching methods. But these are much more general. They just require you to have sparsity. We require more structure. But you see that we can go significantly further and obtain slightly better solutions as well. So again, I just zoomed in into this corner of the plot, and you see that the dimensions we can explore are much bigger, right? And the quality of the solutions is diverging a little bit, but the gap is still considerably small. All right, so what is the secret sauce here? Essentially, the idea that we're able to consider these structured instances and reduce the number of constraints we need to solve these convex optimization problems. And we then, the working horse of our quantum algorithms are then so-called Gibbs samplers, which are methods to compute properties of these so-called thermal states. And this plot I showed before was generated using tensor network methods, and which can efficiently simulate, for instance, quantum Gibbs states of 1D systems, which is what we were essentially doing there behind the scenes. But if you have access to a quantum computer, we actually expect to be able to simulate much larger classes of quantum Gibbs states, which means that you could unlock significantly more classes of optimization problems for which our techniques apply. So already with tensor networks, you can solve some interesting things. With quantum computers, we could do even more. Now, I mentioned a few times that we have these highly structured instances, and you could say like, well, do they pop up in practice? And the answer is, so far, we haven't been able to find like instances you would care about in practice that precisely satisfy all the assumptions we need. But there are examples that satisfy them approximately. And we also have compelling numerical results that show that also for such instances, we also outperform state-of-the-art. And these are so-called Kronecker graphs. So instances on Kronecker graphs, and they show up in various problems related to network optimization. And just to mention, of course, that there is no reason to use our methods as well. If you're considering, let's say, problems with a few thousand variables, then other methods will perform better. The reason to use them is really if you are looking at huge instances. And as you could tell, we will maybe for smaller instance sizes, a heuristic solver will perform better, but we can go to larger sizes and still get a pretty good solution, right? This is essentially the message of this plot over here. So if you're happy with a pretty good solution, then these methods should also give you something. Now, I should also say that if you just look at random instances, say that don't have any particular structure or recurrence relation, this will not work better than like solvers that just sparsity will be better. And I also we still don't have a complete proof that our results will always give you sort of good enough solutions. This is just something we observed numerically so far. And as I mentioned before, we are in the process of finding real world instances where our assumptions apply approximately. And yes, so what are the key takeaways from this talk? Well, that we can, with our methods, you can solve huge semi-definite programs if we have some special structures present in the problem and get pretty good solutions for combinatorial optimization problems that are very big. That we can, that combining these ideas from mapping to quantum Gibbs states and using methods to simulate these quantum Gibbs states on the classical computers, we already can do very interesting things like solving very large problems. However, again, if you gave me a big quantum computer, this would give us even more problems we could solve using these techniques. And I should say again that it would already be sufficient to have maybe, let's say, between 50 and 100 qubits that work really well to play with these algorithms and get something non-trivial. So I think this is another nice feature of these algorithms we developed here, because I don't think we have many applications beyond simulating physical systems for these sort of quantum computers that have between 50 and 100 qubits. Yeah, I think these are sort of, well, some of the nice features of our work. And I should say that unfortunately this work is still not on the archive. Hopefully it will be there soon. And yeah, be happy to take any questions there are from the audience.